Okay, so the one that I want to start is the transportation to finish this topic altogether. The reason I sent to you, I don't think you have this with this green area beforehand. And you'll see that it's just the same transportation with a twist. And I wanted you to see that. So let me just connect it to the discussions prior to this. And this was about the unbalanced transportation problem. Go one step further. Here is the transportation problem you've seen plenty of times before, and it's all balanced of 50 supply by 50 demand. This one we did already, and it's balanced, so we could replace those signs here with equalities. Because the total supply equals to total demand, then you must use all the capacity and you must meet all the demand exactly by the measure. Then here I'm showing to you something I do want you to know how to do. It's the setup of the transportation problem. Sorry, and therefore, and there later also the assignment problem in a transportation table format. And there in assignment, it's called assignment table format. The first here, I relate to the linear programming format, which is the linear programming setup. So that's how I distinguish between the two of them. If I want you to do one of them, I'll tell you. This is the linear programming. This is the transportation table format. And it's only good for problems where the data can be organized in a rectangle. So transportation and assignment is two typical such problems. Not all the problems like production that we had before, it's hard to organize it this way. But whenever you can, it's advantageous because now you can include in such a table hundreds of variables on one screen and solve a very large problem with no problems. You cannot do it when you have hundreds of variables and you want to place all of them in one line. That's why I want to use. Also, there is the issue of balancing the table when it is unbalanced that I want to mention to you now. And this has to do with adding a dummy column or a dummy row that will balance the table. Once you balance the table, the transportation that started unbalanced becomes balanced. And you solve it as if it was a balanced problem when all the constraints are now equal to. So the original problem used to be 20 units here supply. Now it's 30. There is no change here in the total demand. So it's 50 here, but it's 60 here. Supply exceeds demand. If you ignore this column, you see that you have an unbalanced transportation table. So the method is calling for balancing it using a dummy column. And that's very automatic and it is giving beautiful results very easily. In this case here, when you compare the total demand, 50, total supply, 60, supply exceeds demand. In order to make it balanced, you have to add to the demand 10 units. So it means you have to add a column here whose demand is 10. But this demand point does not exist. It's only because you want to mathematically balance the transportation table that you add it, and it becomes very useful. So you pretend you have a destination point called dummy. You don't ship there. So therefore, the shipping cost from source one to that destination is 0. There is no such shipping. If you ship and put units there, you don't want these shipments to add to the total cost because it's not a real shipment. And you put a cost of 0 here and a cost of 0 here from the two supply points to the dummy. The demand of the dummy is 10. And now ignore everything else, realize that you have created a balanced transportation table of 60 by 60. Solve the problem with equality constraints, it's balanced. And realize that the optimal solution will put 10 units here or combined, because the constraint is equal to, and it's equal to 10. So you are going to have shipments here, but it will cost you 0 because the 0 cost is what you put. So what else will happen? The minimization mechanism will minimize the whole table. It will find a transportation plan that minimizes the whole table. This, by definition, will be 0. So it will minimize the rest of it. But hey, this is the original problem. So you get a solution to the original problem that now is unbalanced using a balanced table. That's a little trick. So if you have a solution, let me create a solution now, okay? Just for you guys. I have 2 supply and 4 demand points. And okay, so these are x11, x12, x13, and the new x14, and the others. I'm creating a solution that meets all the demands. This is all equality constraints now. I'll put 25 here. I'm not saying it's optimal. I'm just saying feasible. 25 here, because I have 25 demand here. Yeah, demand, so 25. And the supply is now 30. So I'll put 5 here. Together, 30. Then I don't need on this column anything anymore. And I can't put anything here. It's already 30. I'll put something here. So I'll put here 15. And this way, I satisfied this demand. But the supply is 30. I put here 10. Why? Because I have demand of 10. Together 25. The last 5 will go here. This is a feasible solution. I'm not going to say it's optimal. It's feasible. I just want you to see how you interpret it. Because you have 5 units in the dummy column and 5 units in the dummy column, then this supply point is not using all its capacity. Only 25 units it's from the capacity, 5, there aren't these 5. So you put it on the dummy. And these 5 units and 5 units here don't cost you anything. So you optimized the rest of it. It means that in this solution, both supply points did not work in full capacity. So that's how you understand the solution when you receive it. Fine. Now here is an unbalanced problem with the other side of the coin. Now I put the 20 here. So you have extra demand over only 50 units of supply. So we talked about it last time. Of course, we are going to get a shortage. The question is where. And so now when you draw the original table, it does not include a dummy row. So you look at this, you see 50 here and 60 here. So I need to balance it by adding supply. I put 10 here. And add now a row. It's a dummy supply point. It is shipping 10 units in all, but actually it's not shipping it. But you pretend it is and place a cost of 0 for these shipments. So it will not affect the total cost. What will happen is that the rest of the shipments will be made by this partial table using 50 units of capacity. So you satisfy only 50 of the 60 here. And the rest, the 10 units missing, will be placed in this row, somewhere here. And the sum will be equal to 10. But it will not add to the cost. So at the end of the day, it will minimize the cost of these shipments here. So it's the same trick that we used before, but now we added a row and zeros. One change for this is here. So from here, I move into that here. Again, it's a shortage. But now I could evaluate the shortage. I didn't put just 0. I really charged the supply, the plants, for not being able to meet all the demand. 13 units a unit for shortage on demand point number 1, which does not have to be the same as demand point number 2 or 3. So these are unit shortage costs. That's what it represents. But now the table is really balanced because we added here, it's not even, yeah, it's a dummy supply point, but it has a physical damage. It is evaluating the damage. So it's not a supply point, it's coming instead of what supply is not being shipped. And every unit is penalized. So now you have a transportation table that includes shortage costs in them, and the supply of this shortage is 10 units. And the problem now is balanced. And you solve it therefore as equality all along. And we get a solution. If at the end you get a solution that places, say, 10 units here, that is the new table of the variables, I place 10 units in this cell. One, it's 3 by 3, right? Okay. Let's assume in the optimal solution, I find 10 units here. So what does it mean? It means that this demand point will have a shortage of 10, but is it possible? Because the demand is 20. So if shortage of 10, you have to have a 10 here somewhere. Let's say 10 will be here. Now the sum is indeed 20. But these 10 of those come from shortage. So the demand here is really not satisfied. It will be 10 units in short. The others will be satisfied though. And 10 units short is enabled by the new column that I call dummy supply. It is a dummy supply, but it's a real non-shipment that has a cost associated with it. So this is the difference between the two formulations. They are dealing with the same issue. Now, this one, I think I'll come back at the end. I'll just tell you what the story is. In fact, I can talk about it now. It's not even a problem. I will focus on the linear programming of it, how to translate it into a table format or transportation format. We can delay to later. The surplus exceeds demand. It's the same issue as we have here. See, surplus. So I stay with the same arena. Now, if surplus exceeds demand, you didn't need all the capacity here. Not surplus, I mean supply exceeds demand. If supply exceeds demand, you didn't need all the supply. But what if the demand that you are meeting, which is 25, 15, and 10, is the minimum demand that you have a contract to meet? The only thing left is for you is how best to ship to minimize your cost. But you have to satisfy those values. Then, because you have more capacity, you can sell the extra units in the free market in the same demand points. 3 cities, but you can sell in these 3 cities more than what the minimum demand. in city number 1, you can sell more than 25 units, but the price that you will get for the extra units will be lower than the price that you can secure in the contract. So you can translate additional a lower price to additional transportation cost. So if this was 14 for the shipping from S1 to D1, you see X11, and it was $14, and you can see it in the table here. You see 14. So if this was 14, now it becomes 17 between the same two locations. One is the plant, and one is the same demand, only that I call it Y. It's demand point number 1. I call it Y to separate it from the shipments at the cost of 14, and the cost now is 17, because you sell for a lower selling price. And here it's 17 because it used to be 16. So here you sell by $1 less. And here you will sell by $3 less because 7 goes to 10. And those corrections here are equivalent to the first 3, only in a different, coming from a different supply point. So I added more decision variables to the problem that represent shipments over and beyond the minimum required. I needed this because the unit cost of shipping those units is different than the unit cost of shipping these units. So now I have a larger problem to solve. And the objective function, you understand, have more coefficients. These are the new coefficients. The constraints didn't change. These 3 represent shipping from supply point number 1. But you have to be careful. These are the shipments to meet the regular demands, plus the shipments to meet the aftermarket, I call it, demand. Well, this would constitute 30 units of capacity together, not only the X and the Y. Same you do here. That's from supply point number 2 and supply point number 2 for the new demand. Now, again, it's 30, okay? And now shipping to demand point number 1, now you have to separate. Shipping under the first condition is X11 and X21. That's to meet the demand of 25. But from the same demand point, to meet the secondary demand, you go under the Y11 and Y21 to meet the 10 units. Now, what is the 10 units? Because you have extra supply of 10 units, you have to make it possible for each demand point to receive 10 units. You don't know how the demand is going to be shipped. I'm talking the extra demand. So you have to allow all of them to receive additional 10 units. Maybe one of them will receive it and the others will not. Maybe it will be divided between 2 of the demand points and the third one will not, or maybe between all the 3 of them. But you have to allow this to happen if you don't want to lose an optimal solution. So what do? You write the extra supply that you have here as an additional possible demand. And it belongs to D1 and D2 and D3. Okay, so now the solution, because now you have more demand than supply, will use all the 60 units of the supply, and the demand is this, 25 plus 30. This is the demand. Not all of it will be satisfied. Of this, only 60 units will be satisfied. So you have to allow it to happen. How? You write less than or equal to on those. This will be equal to because you must meet this demand. This will be less than or equal to because you don't know where it will be less than 10. and you allow the 10. So this is the logic of building this linear programming model. And so I wanted you to see that. They say similar logic is applied here when you build a transportation table. I don't want to spend time on that here, but you are more than welcome to see what I did exactly. This one is demand point one, number one, and this one is number one. The cost is 14, the cost is 17. I added columns here. I added a dummy row here. So you may want to understand the concept, but it will be enough if you will know how to do this. You know what? I'm doing it not to intimidate you. I do it for one reason. Transportation as well as assignments can take variety of scenarios in the real world and easily formulate them as linear programming models. And they come up with very useful, beautiful solutions that nobody would expect. Because it can solve very, very large problems. That's why. So that's what I want you to see on this stuff. And I will move on now to the assignment problem that my recollection is you've seen before. I just want to add one, something to it, two things. Who can tell me, did you see this problem on our last meeting?
Yeah.
Oh, we did that, right?
Yeah.
So what we did in the last problem was, and then correct me if I'm wrong, it was the balance problem that you see the solution for on the page here. This is the balance problem, isn't it, that I talked to you about last time? That it was 5 by 5. You just have to remind me, that's all.
Yeah, that's what I have.
And nothing more than that.
Nope, that's it.
Okay, that's why I stopped the class. Okay, good. And I said I want to come back to it in order to add something to this. So what I want to make this balance problem, and maybe I'll remind you what the problem is, so I'll save the reading for home for you. It's that you have 5 assembly lines, and they look for services of inspection from 5 inspection centers. Each inspection center only can serve 1 assembly line, and each assembly line needs exactly 1 inspection center because of the way the devices produced are separated among these assembly lines and because of the expertise that each inspection center has developed. That's why it's go one-on-one. And now the question is how best to assign it in terms of shipping units from the assembly lines to the inspection centers inside the limits of the plant. A lot of traffic there, so you want to minimize the traffic. So the numbers here are the minutes it takes from each assembly to each inspection center, and you want to minimize the total. So here you have a solution for this problem. As you see, I didn't even bother to start here the linear programming nature of this problem as a linear programming model like I did with the transportation, because there I have only 6 variables. Already here I have 25. 5 by 5. That's a large table. Maybe I can put 25 variables on my long screen. I'm not sure how many of you can. And nobody does it. The better way is to organize it in a rectangle here. In fact, it's a square. It's not a rectangle. Enter all the data here in this format. Create a new table for the variables here. Sum all the rows here. See? To represent the assignments of inspection centers to 1 assembly line. And then sum all the columns here to represent the assignments of all assembly lines to a single inspection center. Make constraints of the form. These sums are equal to 1, and these sums are also equal to 1. Balanced, solve the problem by minimizing the time, get 55 minutes. And this is flash time. Now I'm saying next week, line number 5, not line, the inspection center number 5 is going to be down because of maintenance, repair. So suddenly the problem becomes unbalanced. And that's right now the name of the game, how to solve an unbalanced problem. Well, we still have 5 customers, but only 4 inspection centers, only 4 of them. I have to change the model now because I know that one of the assembly lines is not going to work next week. That's a horrible solution for management, but that's the situation now. So let's say we eliminate this inspection possibility. We don't know which one of those needs to be eliminated. We want the solution to tell us. So just from the perspective of transporting time from assembly line to inspection centers, what's the best solution? Management might not take this solution. They might decide that this assembly line that you are recommending not working next week is producing a product that with high demand in the market, and we are not going to shut it down. So they will tell you that. But just from the perspective of the shipping time. So how do we change the model? One of these constraints here, constraint number 5, needs to be eliminated. So what I'll do to make the changes as little as possible, I'll write 1, 1, 1, 1, 1. That's the original problem. And now I'll make this one equal to 0. I'll keep the constraint, but I'll force it to be 0. Instead of deleting variables and so on. I'll keep all the variables, but I know that those variables are going to be equal to 0 because of the constraint. I'll keep these constraints, all of them, but I'll have to change something. Maybe I'll ask you guys, maybe someone can, in class, I would stop here and ask, what is the change that I have to make on the constraints here versus here versus the one here, so that the solution will not come as infeasible? What should I do? Okay, remind you that the constraints right now are, all of them are equal to. These, all the 5 constraints are equal to 1. Now, what should I do in order for this to have a solution? If I leave it this way, I'm telling you, it will have no solution. Anybody can tell me why? No one.
Do you make it equal to 2?
What will be equal to 2? This one here?
Yeah.
And this means that you want the shipments or the services from each center here. So you want 2 centers be serving number A, and 2 centers be serving number B. That's what you are telling me, if it's 2 here. Of course, that's not what you meant.
Yep, never mind.
Anyone? Well, is it clear to you that one of those must be 0 because this one will not be needed? We only have 4 assembly lines, so only 4, not as 4 inspection centers, so only 4 assembly lines are needed. But which one? I want the model to tell me which one. Anybody wants to say, make a correction now? How about changing this to less than or equal to 1? So 5 constraints, all of them are less than or equal, each one is less than or equal to 1. So one of them is equal to 0. I'll make those here equal to 1 because I want all the 4 inspection centers to keep working. But I will allow one of the assembly lines be equal to 0. So I'll write less than or equal to 1. So I know that exactly 4 of the 5 will be equal to 1 because I have exactly 4 assembly inspection centers. So these are the changes. And what will happen, it will tell me which one of the assembly lines I have to shut down because I know that this one is shut down. Okay. So let's see. The objective will remain the same. Minimization remains the same. Variables I'm not changing because I'm including the last row as a variable, although I force it to be equal to 0. So variables don't change. It's 14 to G18, yes. Now here, what is this? These are the assignments of inspection centers to an assembly line. So this is where I'm changing it to less than or equal to 1. So this is the less than or equal to 1. See, all of them. And now I go to the second one and making a change here. Right now, I included 5 constraints. I'm still going to include 5 constraints, but one of them changed from 1 to 0. It remains equal to because I want all the assembly lines that are left be assigned, and it's all equal to 1. So now I made the problem, it's unbalanced, but I allow it to be balanced because of the less than or equal to 1 thing, and I solve the problem. And the solution, and this, oh, did I change it to 0? I don't know. No, you see, I didn't do the right thing here. I didn't change something very important. I didn't change this column. So the 0 is still 1. Here's why. I think we are talking this one. Let me show you. Change. I did change the left-hand side, the sign to less than, but I kept the 1 here. So instead of 1, I have to enter the column, and the column includes the 0. And now, when I resolve it, it's give you an infeasible solution, and it's not true. It is feasible, and I saw that my solver is doing it more than once, that it gives me infeasible. There is nothing infeasible here. Now, I have a problem with solver. Anyway, let me explain to you what I should have received. Okay, so what it tells you here, do not use assembly line 0, E, do not use it at all. This one, it puts a 1 here, although, okay, let's see why. Yeah, puts a 1 here, it should not. So it's not doing what it's supposed to do. It did it before class, and I know that my solver is giving me some hard time sometimes. So what I should have received is 1 here because of the 1 here, and 0 here because of the 0 here. And in my solver, there is a bug. So that's what I should have received. If I received the right thing, I'll put 1 here. Let me do it. I'll get a 0 here. And let's see, if this is all 0, so where is the, see what it does? It's not solving, it should put, it cannot put zeros here at all. It's screwing it up. I don't know why it's doing it. Let me see something. Maybe I made a mistake here. Change. So these are okay. And it's going from G19 to C19 to G19. C19 to G19, this is correct. These are the sum values. And it has to be less than or equal to, yeah. Okay, this needs to be 1 here. They're all 1. I think I corrected it wrongfully. These are all less than or equal to 1. But this one here, okay, I think I see what. Change. Yeah, that's where the problem. I corrected the wrong constraint. So my solver did not do any bad things here. Okay, here. Now it's good. Here. That's what I wanted to get. So indeed, assembly line E is not working. And this one is the inspection center that is down. And these 4 are working. And all the inspections are working by definition because I make them equal to 1. So that's how you correct a problem like this. Let's say to continue this, management has decided that they cannot afford an assembly line here to not work. So what they decided to do to allow 1 inspection center that is still working to serve 2 assembly lines. But they didn't decide which one. They give you 2 options. They say either this one that is inspection number 1 or inspection number 2, out of the 4, only one of them will be working with 2 assembly lines. This way it will be all the 5 can be served. And they ask, well, which one do you prefer? And you are the operation manager. So you say the one that gives me more time saving, or the one that costs me less in time. So you'll solve it twice. One time you'll put 2 here, and 1, 1, 1. Make the problem balanced now because you can serve 5 lines. So don't write less than or equal to, write equal to 5. So this one also will be assigned. And then you solve it again with 2 here. And again, and this will be 1 now. And you see which one comes with the shortest time. And this is the one you will recommend to management. So I'm sorry about the confusion before, but we are good now. And that's what I want you to see on this assignment problem. And then at home, please read part B and do it yourself. It's quite easy. So this was the assignment. There's not much for me more to say about it. I want to move to another type of problems. And I'll take a production problem from the review file that I sent to you. But I added a problem that you don't have there, so pay attention. I'm going to upload it anyway. Okay. Okay. So this is the file called LP review. You may recognize all those problems. And by the way, this one I called before production 2, but it's actually management, so I changed the name here. I added problem number 3. That is the one I want you to see. And you have an investment problem, you have transportation 1, you have transportation 2. I didn't think, and you have diet. Diet is just a blending problem, because you have to come up with a diet with characteristics. It's like the blending problem. And there are two more files, by the way. It's called LP examples and LP example 2 that we worked before with. So you have quite a few examples. They're all Excel files. Now, in this problem, so it's a production problem. I added here a little diagram, if you wish, that explains how the production proceeds here, and then you'll understand why I want you to see it. It's a bit different than the simple production problems that we've done before, in which you have a few products and you have departments, and they have to go through all the department, and you have time available in the department. So they ask how many of each product to produce, and yeah, there is a demand to meet. Very regular, standard questions like this one will be such a problem. This is really a simple, very good practice, by the way, problem that I placed here with sensitivity. This is the model, and here are the sensitivity questions, something that you can expect in the test also. So I'll give you the model and I'll ask you sensitivity questions. In this problem, we have a situation that in part is similar to what you're used to in terms of the constraints, and in part, it's not. It's something a bit new, but if you think in a reasonable manner, you will understand it right away. So this production goes like this. There are 3 drugs that you can sell in the market. It's A, B, and C. The question at the end of the day is how much of each drug to produce. Now, where is the catch? Well, each of the drugs, A, B, and C, are using the labor. Labor is one resource. And this is very regular thing. You have seen it before. And there is a raw material. It's a chemical. You are producing drug. And this is the major scarce resource. So this, if anything, this will limit the production. And you have 350 units available of the chemical. And you have 4,000 hours available of labor. So where is the diff? Okay, there are also required quantities that you have contracted to sell 200 units of drug A and 250 units of drug C. This is, so whatever you do, it has to be more than 200 and more than 250, or exactly 200 and 250. Okay, so these are constraints that are causing no difficulty. You have seen those constraints before. Now come the production process. This production process requires 2 units of A you ship in order to the department of B to produce B out of it. So in order to produce B, you need a chemical, but you also use A into it. You modify A, and then it comes as product B. 2 units of A are needed for 1 unit of B. That's one thing. In addition, to produce C, you ship B into it. So you take some of the Bs, you ship it to the C department, and now you produce an item called, drug called C, and you use the chemical for it also. Here you need it 1-to-1. 1 unit of B is needed to produce 1 unit of C. So 2 units of A are needed to produce 1 B. 1 B is needed to produce 1 C. That's it. This means that the quantities that you produce of A, B, C are not independent on one another. The production process requires relationship between them, and these relationships solver doesn't know if you don't tell it that they exist. So these are the additional constraints, and in fact, the additional variables that you need here. You make money by selling the drugs only of those that you yourself sell as independent drug. So A is sold for $30 revenue if you sell it as an independent A. A that you produce and sell it into the B department, I call AB. For this, you don't have an independent profit. So AB is a variable that represents how many units of A you are shipping in order to produce the B drug. Then B is what you produce of the B to sell as B. And BC is how many you ship to the C department. So this is the total amount of A you produce. This is the total amount of B you produce. And C is C, is standalone. But you have to come up with these relationships. So you say the following. The number of units of A that are produced for the B drug, I call it AB, must be equal to 2 times the number of units of B that you sell plus the number of units of B that you produce for the C drug. Example, let's assume I produce 10 units of A that are dedicated for the production of B. Then I can produce only 5 units of B in all. And this is the B plus BC. So that's why these constraints. In addition, now you produce B units that are dedicated for the C product. I call it B for C. They are equal to exactly how many C units of drug C, how many units of drug C you produce. That's in the problem, and you read it, that's the description of the process. These two constraints are the constraints that were new to you. You didn't see them. I produced them here. I wrote here, for this constraint, I have AB, and then I move 2 times B plus BC to the left-hand side so that everything can be calculated with some product. So I wrote it as follows. AB minus 2 times B minus 2 times BC. What you see here is what's written here. And this is now equal to 0. The same I did with the next constraint. So it's BC minus C, it's here, and this one is equal to 0. So these are the two constraints that are additional that you didn't see before. Such constraint will describe a production process even if it's much more convoluted. What if you need to produce C, you need A directly? Not through B, but directly A, because now you mix A and B to create AC with a chemical. So you have to add another variable that is called A to C and a constraint that connects how A to C is related to C. So you can add to this, and it can include many more drugs. Actually, usually it does. And the problem is very versatile. So this is the reason I showed it to you. Let's solve the problem now and do the sensitivity analysis. And there are 2 sensitivity questions here on B and C. Okay, so the model is already in. Let's check so that I am having the correct thing. The objective function, let's see where I put it. Okay, it used to be, okay, the objective function is this one. See, that's the objective function. And it's a maximization of revenue. And N8 to R8 goes from N8 all the way to R8. These are my variables. And then the constraints. So I'll do it this way. I'll check these constraints, see where it is. Not going to change anything. Okay. So the first 3 sum products are equal to the first 3 right-hand side. And this is what this constraint is telling me. There is no change. Constraint number 2 is the next two constraint on the right-hand side greater than or equal to these two right-hand sides. No change. Last is, okay, so last is this one. There is one additional here that hasn't, oh, I know why. Okay, so it's S15, yeah. So it's this constraint. So this one needs to be less than or equal to 350, it's U15. We are good, no change. All what I need is to eliminate this one and now solve the problem. And the sensitivity report I already have, so we'll look at it in a minute. So look what the solution is doing. It's produced this amount of drug A and sell it in the market. Now it's producing more drug A and shift it into a B drug, 961 units. It means that half of it is the number of B units that are produced, and indeed this is what's happening. The total amount of B is this and this. I don't sell drug B in the free market at all. I use it in order to produce C, because you see this one here? This is half of this amount, because you need 2 units of A to produce B. So this is how many units of B I am shifting into a C drug. And so, and it's going on the ratio of 1 to 1. So we have the same number of units here. And this is the revenue they are going to make. That's the solution. And now, as I do that, I'm using all the 4,000 units here because the constraint was equal to, so no wonder. And now let's look at the question on B. The selling price of the 3 drugs are expected to increase. So the selling prices are here, 1 and 2 and 3. 2% in each. And the question is that management is wondering, should they change now their production plan? So you have to check it with the simultaneous changes on the right, on the objective coefficient simultaneous changes. So we have 30 plus 2%, this plus 2%, and this plus 2%. Take a ratio when you divide it by the allowable increase. So we are talking 1, 2, and 3. This is the sensitivity report. So this one is divided by infinity, no problem at all. It's 0. And this one is divided by 4.7. It's a bit more than 0.5, okay. And this one is divided by 110. It's not this one, it's 2% of this one is divided by 110, so it's 2 divided by 110. And that's 2% of 71 divided by 471. And this one I'm not even calculating because I have to divide by infinity. So when you take the 2 ratios and add them to one another, the sum becomes way below 1. And this tells you that the optimal solution remains unchanged. Don't worry about it, management can relax. And the last question here. So management is thinking of adding overtime. They see that they've been using all the 4,000 hours. Even if you allow not all the 4,000 hours be used, and instead of equal here, you wrote here less than or equal to, and solve it again, you will see that 4,000 hours are being used. So that's optimal, not forced on the model. So if management sees that, they think of maybe we can improve our revenue by adding more time. How? Overtime. So now they ask you, okay, we are thinking of adding overtime. Do you think it's a good idea? And you immediately say, yes, the revenue will go up. They ask you, then how much are we going to pay for overtime? Because overtime is expensive. You pay over and above the regular pay to the workers that work in regular time. So you look at the model value that is changing, and it's this value. Now it's a single value. So we don't have the multiple choice and the multiple changes situation. And therefore, you go back to the sensitivity here. You look for the 4,000. And you say, okay, for 1 hour overtime, we can use the shadow prices because of the allowable increase, 600. And 1 hour of additional labor will increase the revenue by $4.28. That is, if this hour doesn't cost you anything. But if it costs you, how much are you going to pay for overtime? So you have what you pay for regular time that is not part of the model. You have to add to it now the $4.28 maximum. Do not pay more than a premium of $4.28 for overtime because you don't get the contribution. That's the maximum that management should be willing to pay for overtime. So that's what I wanted to do today. And I'm encouraging you to do all the problems from the book, as I said last time, even more than 10 questions, because they have some more from 11, 12, and so on. I did all the way to 18, not all of them, because 18 was transportation, and I found it, so I solved it. But you just go over as many problems as you can. Why? I want you to get used to different types of thinking. In linear programming, this is what's the name of the game. You have to know those different cases, different scenarios, and see how linear programming is dealing with it fast. Sensitivity analysis, very important for you to understand. As I said last time, I think I say it again, you will not be required to set up and solve with solver a linear programming problem in order to produce the sensitivity report. I'll give you both the model on, you'll see it in the file. I'll give you the file and I'll give you the results of the computer run, and you'll have the sensitivity report, but you'll have to answer these sensitivity questions. So this way, I will not ask you to spend time on technicalities. And when you do technicalities, then you make mistakes, you have to delete, and you forget whether some product is, and why is it not working, and you forget to press F4, all kind of little things that I've seen time and again. And it's not what I'm testing you on, guys. That's why I don't want you to run it. I know that you'll have to run at home linear programming if you want to practice sensitivity analysis yourself. In the book, they don't give you those solutions. You have to run them. I was so generous, I gave you the sensitivity report, and between the two of us, I should not, because I want to force you to practice it at home. I gave it to you. Here, you have it. See, I'm giving you this. This is what you will get from me in the test. And again, I want you to know you can set up a model as this one here as an answer to a linear programming formulation. If it's possible, and if you want to type it instead of the Excel, type the following, type it this way. If you want to type it this way, go ahead and do it. I'll accept both. This is faster, in my opinion. Most of the students in the past use this trick. Not trick, use this option. I let them do it, and they did it in the test, and it was very fast. Okay, so that's all what I wanted to say. Anything you want to ask me?
Are you going to upload that exact file that you just used?
What about it?
Are you going to upload it? Because the one I have only has like 4 examples. We don't have the latest chemical one.
Yeah, I know. I added problem number 3 that I did today that wasn't in the first version.
Yeah.
And I think this green area of the first one, does it appear there already?
Yeah, I saw it.
Oh, so it was there. Okay, well, then the last problem was not there. And of course, I'm going to, I said so at the beginning, I am going to give you all the files that I have.
All right, thank you.
Okay. Any question? Oh, okay, so let me upload it. And first I have to convert it, and then I'll say bye-bye and see you in on Tuesday. Am I right?
Yep.
Okay, good.
Thank you.
Bye-bye.